Imagine a spacecraft leaving Earth, not for Mars, not for Jupiter, but for another galaxy entirely. The Andromeda Galaxy sits 2.5 million light-years away from us, a distance so vast that it defies everyday comprehension. Yet scientists have begun seriously contemplating what an expedition to this neighboring galaxy might actually entail, and the engineering challenges alone paint a picture more ambitious than anything humanity has ever attempted. The concept of an Andromeda expedition forces us to confront fundamental problems that go far beyond conventional space travel. At the speed of our fastest current spacecraft, Voyager 1, which travels at roughly 38,000 miles per hour, the journey would take approximately 44 billion years. The universe itself is only 13.8 billion years old, which means we would need to travel nearly 3 times the current age of the universe to reach Andromeda using today's technology. This simple calculation reveals why theoretical physicists have turned their attention to propulsion systems that sound more like science fiction than engineering proposals. One of the most seriously studied concepts involves antimatter propulsion. When matter and antimatter collide, they annihilate each other completely, converting their entire mass into pure energy, according to Einstein's famous equation. The efficiency is perfect, 100% mass to energy conversion, making it theoretically the most powerful fuel source imaginable. A spacecraft using antimatter engines could potentially reach 10% the speed of light, reducing the journey time to Andromeda to roughly 25 million years. While still incomprehensibly long by human standards, this represents a dramatic improvement over conventional propulsion. The practical challenges of antimatter propulsion reveal themselves immediately upon examination. Creating antimatter requires enormous amounts of energy, and currently, humanity can produce only infinitesimal quantities at facilities like CERN in Switzerland. To fuel an Andromeda expedition would require thousands of tons of antimatter, an amount that would demand energy production far exceeding the total current output of human civilization. Storage presents another obstacle, as antimatter must be contained without touching normal matter, requiring sophisticated magnetic bottle systems that themselves consume significant power. An alternative approach involves laser sail technology, where enormous laser arrays positioned in space would propel lightweight spacecraft equipped with reflective sails. The advantage here lies in keeping the power source stationary rather than carrying fuel aboard the vessel. Breakthrough Starshot, a real initiative funded by investors, including Mark Zuckerberg and the late Stephen Hawking, proposes using this method to send tiny probe craft to nearby stars at 20% light speed. Scaling this up for an Andromeda mission would require laser arrays spanning areas larger than entire countries, and sails measuring thousands of kilometers across. Perhaps the most exotic proposal involves utilizing theoretical physics that remains unproven. The Alcubierre drive, named after physicist Miguel Alcubierre, would create a bubble of warped space-time around a spacecraft, contracting space in front of the vessel while expanding it behind. The ship would surf this wave of space-time itself, potentially exceeding light speed without violating Einstein's relativity, since the craft itself would remain stationary within its bubble. The energy requirements for this approach proved initially astronomical, but subsequent refinements by NASA physicist Harold White suggested that optimizing the bubble geometry might reduce the energy needed to something merely equivalent to the mass energy of Jupiter. The problem with exotic propulsion like the Alcubierre drive extends beyond energy requirements into the realm of exotic matter. Creating the necessary space-time warping would require negative energy density, a form of matter that may not exist in our universe. While quantum field theory suggests negative energy densities might be possible through phenomena like the Casimir effect, no one has demonstrated how to generate and manipulate these forces on the scales needed for spacecraft propulsion. Time dilation effects on an Andromeda expedition introduce philosophical and practical complications that mission planners would need to address. Even if a spacecraft could achieve 90% light speed, relativistic effects would mean that travelers aboard would experience time differently than people remaining on Earth. A journey that takes millions of years from Earth's reference frame might feel like only thousands of years to the travelers, though this hardly solves the problem, as thousands of years still far exceeds human lifespans and even the longevity of human civilizations. This temporal discrepancy leads to considering generation ships, vessels designed to support multiple generations of human inhabitants during the journey. The engineering requirements for a self-sustaining artificial ecosystem capable of supporting human life for millennia present challenges we have barely begun to understand. The ship would need to recycle air, water, and nutrients with near-perfect efficiency, as resupply would be impossible. It would need to maintain genetic diversity in its human population to prevent inbreeding, requiring either a large initial population or advanced genetic management techniques. Radiation shielding becomes critical for any expedition lasting millions of years. Cosmic rays and high-energy particles permeate interstellar space, and without Earth's protective magnetosphere and atmosphere, crew members would face continuous bombardment. Traditional shielding using heavy materials like lead would add prohibitive mass to the spacecraft. Alternative approaches include using water, which serves double duty as both radiation protection and consumable resource, or generating artificial magnetic fields to deflect charged particles, though this requires substantial ongoing power generation. The spacecraft structure itself must withstand millions of years without catastrophic failure. Materials degrade over time through processes like metal fatigue, radiation damage, and micrometeorite impacts. Even minor damage accumulates, and in the void between galaxies, no repair materials exist beyond what the ship carries. The vessel would need either materials science far beyond current capabilities or robust self-repair systems, potentially involving advanced robotics or even self-replicating machines that could manufacture replacement parts from harvested asteroids during the early stages of the journey. Navigation across intergalactic distances poses unique challenges distinct from interstellar navigation. The Andromeda Galaxy appears as a fixed point in our sky, but it actually moves at roughly 70 miles per second toward the Milky Way. Over millions of years, its position will shift significantly. The spacecraft's navigation system would need to continuously adjust course, requiring autonomous decision-making capabilities, as communication with Earth would become impossible once the ship traveled even a fraction of the distance. Communication delays illustrate another profound aspect of this journey. Light itself takes 2.5 million years to travel from Andromeda to Earth. A message sent home from a spacecraft, even 1% of the way to Andromeda, would take 25,000 years to arrive, and the response would take another 25,000 years to return. The expedition would be fundamentally alone, unable to request assistance or guidance from Earth. Any decisions about scientific discoveries, course corrections, or mission changes would need to be made by the crew or autonomous systems without input from home. The space between galaxies differs fundamentally from the space between stars. While interstellar space contains thin gases, dust, and occasional stellar objects, intergalactic space represents some of the emptiest regions of the universe. The density of matter drops to nearly nothing, with atoms separated by meters or even kilometers. This emptiness would make resupply impossible, as the ship could not harvest materials encountered along the way. Every atom needed for the mission would need to be carried from the beginning, or produced through onboard nuclear fusion. Energy generation over millions of years requires technologies that do not degrade or deplete. Solar panels become useless once the ship moves far from any star. Nuclear fission requires uranium or plutonium fuel that would need to last the entire journey. Nuclear fusion offers more promise, as hydrogen constitutes the most abundant element in the universe, and the ship could theoretically harvest it from the thin interstellar medium. However, the engineering challenges of maintaining fusion reactors for millions of years without replacement parts from Earth remain daunting. The psychological aspects of an Andromeda expedition challenge our understanding of human nature and society. Generations would be born, live, and die aboard the ship, never seeing Earth or their destination. These middle generations would exist solely as links in a chain, their purpose entirely defined by a mission they did not choose and a goal they would never witness. Maintaining cultural knowledge, technical expertise, and mission dedication across thousands of generations would require social engineering and educational systems, unlike anything humanity has developed. Cultural drift over millennia could fundamentally alter the mission itself. Languages evolve, traditions change, and knowledge can be lost. The descendants of the original crew might develop beliefs and values entirely different from those who launched the mission. They might decide to turn back, to divert to a closer destination, or to simply drift through space indefinitely. Without enforcement mechanisms from Earth, the mission remains entirely at the mercy of future generations' choices. Scientific observations during an Andromeda expedition would revolutionize astronomy and cosmology, even if the ship never reaches its destination. The journey would provide unprecedented data about intergalactic space, cosmic background radiation, dark matter distribution, and large-scale structure of the universe. Instruments aboard could make measurements impossible from within a galaxy, potentially answering fundamental questions about the nature of space, time, and matter. The Andromeda Galaxy itself presents a worthy destination for such an ambitious journey. It contains approximately 1 trillion stars, more than twice the number in our Milky Way. Its spiral structure spans roughly 220,000 light-years, making it the largest member of our local group of galaxies. When viewed from Earth, Andromeda appears as a faint smudge of light, but upon approach, it would reveal itself as a magnificent spiral of billions of stars, a sight no human eyes have ever witnessed up close. Within Andromeda lie countless worlds, planets orbiting those trillion stars. Statistical analysis suggests billions of these planets might exist in habitable zones where liquid water could exist. Some might harbor life, perhaps even intelligent civilizations. An expedition to Andromeda would provide the first opportunity to study exoplanets in another galaxy, to compare planetary systems formed in a different galactic environment, and potentially to discover life that evolved entirely independently from terrestrial biology. The globular clusters surrounding Andromeda number in the hundreds, each containing hundreds of thousands of ancient stars. These dense stellar cities offer glimpses into the galaxy's formation and evolution. Some of Andromeda's globular clusters orbit in a plane perpendicular to the galactic disk, suggesting they may have been captured from smaller galaxies that Andromeda consumed in its past. Studying these structures up close would illuminate the processes of galactic cannibalism and growth that shape the largest structures in the universe. Andromeda's central supermassive black hole possesses a mass equivalent to 100 million suns, concentrated in a region smaller than our solar system. This monster shapes the galaxy's core, its gravity influencing the orbits of millions of nearby stars. Observations from within Andromeda would allow unprecedented study of how supermassive black holes affect their host galaxies, how they feed on surrounding matter, and how they drive the energetic phenomena we observe in galactic nuclei. The collision between Andromeda and the Milky Way, predicted to occur in roughly 4 billion years, adds urgency to the idea of an expedition. When these galaxies merge, they will create a single giant elliptical galaxy that astronomers have nicknamed Milkomeda. Studying Andromeda now, before this merger, would provide baseline data for understanding how such cosmic collisions unfold. Though individual stars likely will not collide due to the vast spaces between them, the gravitational interactions will dramatically reshape both galaxies. Dark matter comprises the majority of mass in Andromeda, just as it does in our Milky Way. This invisible substance reveals itself only through gravitational effects on visible matter. An expedition to Andromeda would traverse vast halos of dark matter, potentially providing the first opportunity to study this mysterious substance from within. Instruments designed to detect dark matter particles could operate far from the confounding signals of Earth's dense matter environment. Satellite galaxies orbit Andromeda like moons around a planet. More than 20 of these smaller galaxies have been identified, gravitationally bound to Andromeda and orbiting within its dark matter halo. The largest, Messier 32, contains several billion stars and orbits close enough to Andromeda that tidal forces are distorting its shape. These satellite galaxies provide natural laboratories for studying galaxy evolution on smaller scales. Star formation in Andromeda proceeds at a different pace than in the Milky Way. Some regions of Andromeda show vigorous starbirth, with hot young stars illuminating vast nebulae of gas and dust. Other regions appear quiet, their star formation having ceased long ago. Understanding why different parts of the same galaxy exhibit such varied behavior would advance our knowledge of the processes that govern stellar birth and the evolution of galaxies as a whole. The spectral analysis of stars in Andromeda reveals chemical compositions similar to those in the Milky Way, suggesting that the processes of nucleosynthesis operate identically across cosmic distances. Elements heavier than hydrogen and helium form in stellar cores and scatter through space when stars explode as supernovae. Generations of stars have enriched Andromeda with these heavy elements, creating the materials necessary for planet formation and potentially for life itself. Variable stars in Andromeda, particularly Cepheid variables, helped Edwin Hubble determine in 1923 that Andromeda was actually a separate galaxy rather than a nebula within the Milky Way. These stars pulse with regular periods related to their intrinsic brightness, allowing astronomers to calculate their distances. An expedition to Andromeda would allow direct study of these stellar lighthouses and potentially discover new types of variable stars unknown in our galaxy. Binary star systems abound in Andromeda, as they do throughout the universe. Pairs of stars orbiting each other can produce spectacular phenomena, from eclipsing binaries that dim and brighten as they pass in front of each other, to contact binaries where two stars literally touch, sharing their outer atmospheres. In some cases, one star strips material from its companion, leading to nova explosions or the formation of compact objects like neutron stars and black holes. Planetary nebulae in Andromeda mark the deaths of sun-like stars, their outer layers blown off to form glowing shells of gas surrounding the hot stellar cores. These beautiful structures exist only briefly in cosmic terms, a few tens of thousands of years before dispersing. An expedition would encounter thousands of these objects at various stages of evolution, providing snapshots of stellar death and recycling of matter back into the interstellar medium. Supernova remnants scattered throughout Andromeda trace the violent deaths of massive stars. These expanding shells of gas, heated to millions of degrees by shock waves, shine in X-rays and radio waves. They enrich the galaxy with heavy elements forged in the moments of stellar collapse and explosion. Some remnants contain neutron stars, or stellar mass black holes, the compressed cores left behind when the outer layers blew away. Dust lanes threading through Andromeda's spiral arms block visible light, but glow in infrared wavelengths. These regions contain the raw materials for new stars, giant molecular clouds, where gravity gradually compresses gas and dust until nuclear fusion ignites. An expedition equipped with infrared telescopes could peer into these stellar nurseries, watching stars being born in real time across millions of years of observation. The rotation of Andromeda follows patterns that reveal the distribution of matter within the galaxy. Stars in the outer regions orbit faster than visible matter alone could account for, providing some of the strongest evidence for dark matter. Detailed measurements from within the galaxy would map dark matter distribution with unprecedented precision, potentially revealing clues about its nature and properties. Thank you for listening to this exploration of what an expedition to the Andromeda Galaxy might entail, and what wonders await in that distant realm of stars.